unprecedented shape characteristics. Each line of evidence independently suggested that Oumuamua was extraordinary, and the combination created an overwhelming case for its anomalous nature. Advanced computer modeling attempted to reconcile Oumuamua's various observed properties through comprehensive simulations that incorporated multiple physical processes simultaneously. These models tested whether combinations of conventional astrophysical processes could produce an object with Oumuamua's observed characteristics, including its extreme elongation, acceleration behavior, and surface properties. While some models could reproduce individual aspects of Oumuamua's behavior, none successfully explained all of its properties simultaneously using conventional physics. The modeling efforts revealed fundamental tensions between different aspects of Oumuamua's observed properties. Models that explained its acceleration required composition or structure inconsistent with its thermal properties. Models that accounted for its shape suggested formation processes incompatible with its spectroscopic characteristics. Models that explained its interstellar trajectory implied modification processes that should have altered other observable properties in ways that weren't detected. Isotopic analysis, while limited by the brevity of observation time, searched for chemical signatures that might reveal Oumuamua's stellar origin. Different stellar environments produce distinctive isotopic ratios in their planetary systems due to variations in stellar nucleosynthesis, supernova enrichment, and cosmic ray exposure. However, Oumuamua's rapid passage through the inner solar system prevented the detailed spectroscopic observations necessary to detect isotopic signatures that might identify its stellar birthplace. The limited isotopic data that was obtained showed ratios consistent with solar system materials, but the measurement uncertainties were too large to definitively determine whether Oumuamua's composition matched solar abundances or represented materials formed in a different stellar environment. This ambiguity left open the possibility that Oumuamua contained chemical signatures of alien stellar processes, but the evidence remained tantalizingly incomplete. Dynamical analysis examined Oumuamua's past trajectory to determine its possible origin region within the galaxy. By working backward from its observed motion and accounting for galactic rotation and stellar motion, astronomers attempted to identify which stellar regions Oumuamua might have visited during its interstellar journey. However, the chaotic nature of galactic dynamics and the long timescales involved made it impossible to definitively trace Oumuamua's path back to its origin. The dynamical analysis did reveal that Oumuamua's velocity relative to the local standard of rest was unusually low for an interstellar object, suggesting either that it originated from a nearby stellar region or that it had experienced gravitational encounters that modified its velocity during its galactic journey. This relatively low velocity implied that Oumuamua might have spent more time in the local galactic neighborhood than would be expected for objects ejected from distant star systems. Polarimetric observations measured the polarization characteristics of light reflected from Oumuamua's surface to determine information about surface texture, composition, and particle size distribution. These observations revealed polarization properties that were generally consistent with rocky asteroid surfaces, but with subtle differences that suggested either unusual composition or surface modification during interstellar exposure. The polarimetric data indicated that Oumuamua's surface had been modified by space weathering processes, though the degree and type of modification were difficult to determine from the limited observations. Space weathering typically darkens and reddens asteroid surfaces through micrometeorite impacts and solar wind exposure, but the effects of interstellar space weathering over millions of years might be quite different from solar system space weathering processes. Magnetic field measurements attempted to detect any magnetic signatures that might provide information about Oumuamua's internal structure or origin. However, the object was too distant and moving too quickly for sensitive magnetometer observations, leaving questions about its magnetic properties unanswered. The absence of magnetic field data was particularly frustrating since magnetic measurements might have provided unique insights into Oumuamua's formation environment and internal composition. Seismic analysis techniques, typically used to study asteroid internal structure through impacts or tidal forces, were impossible to apply to Oumuamua due to its rapid passage through the solar system. The lack of seismic data meant that fundamental questions about Oumuamua's internal structure, density distribution, and possible internal cavities or layering remained unresolved. Chemical composition analysis relied primarily on spectroscopic observations that provided limited information about surface materials, but revealed nothing about bulk composition or internal chemistry. The spectroscopic data suggested surface materials similar to carbonaceous or organic-rich compounds, but the signal-to-noise ratio was too low for detailed mineral identification or chemical abundance determination. Atmospheric analysis searched for any evidence of gas emissions, dust production, or atmospheric phenomena around Oumuamua that might explain its acceleration or provide information about its composition. Despite using some of the world's most sensitive atmospheric detection instruments, no evidence was found for gas emissions, dust clouds, or other atmospheric activity that typically accompanies comet activity. The absence of detectable atmospheric activity was particularly puzzling given Oumuamua's acceleration behavior. Theoretical calculations showed that the observed acceleration would require gas production rates that should have been easily detectable with available instruments, yet no such gas production was observed. This contradiction between expected and observed atmospheric activity became one of the most challenging aspects of Oumuamua's evidence profile. Surface composition mapping attempted to identify spatial variations in composition or properties across Oumuamua's surface that might provide clues about its formation history or internal structure. However, the object's rapid rotation, great distance, and limited observation time prevented the detailed surface mapping that might have revealed compositional heterogeneity or surface features. The lack of surface detail was particularly frustrating since surface mapping might have revealed evidence of impact craters, geological structures, or artificial features that could have provided crucial information about Oumuamua's origin and nature. Without surface detail, fundamental questions about whether Oumuamua was a single coherent object or an aggregate of smaller components remained unanswered. Gravitational perturbation analysis examined whether Oumuamua's acceleration might result from previously unknown gravitational effects, exotic matter distributions, or modifications to gravitational physics on small scales. While these analyses found no evidence for exotic gravitational phenomena, they also revealed that conventional gravitational physics provided no explanation for Oumuamua's observed acceleration pattern. The gravitational analysis also examined whether Oumuamua might be influencing the orbits of other solar system objects through gravitational interactions. However, Oumuamua's small mass and brief visit made any such gravitational effects undetectable with current measurement precision, leaving questions about possible gravitational anomalies associated with the object unresolved. Comparative planetology analysis examined whether Oumuamua's properties might be explained by formation processes that operate in exoplanetary systems with different characteristics from our solar system. Recent discoveries of exoplanetary systems with hot Jupiters, super-Earths, and other planetary types not found in our solar system suggested that planet formation can produce objects with properties not represented among solar system objects. The comparative analysis revealed that some exoplanetary formation scenarios might produce objects with characteristics similar to Oumuamua's observed properties, including extreme elongation resulting from tidal disruption events, unusual composition resulting from formation in different stellar environments, and acceleration mechanisms resulting from sublimation of exotic ices or interaction with stellar radiation fields different from our Sun. Collision modeling examined whether Oumuamua's unusual properties might result from collisional modification during its interstellar journey. Computer simulations tested whether impacts with interstellar dust, collisions with other interstellar objects, or passage through dense interstellar clouds might alter object properties in ways that could explain Oumuamua's observed characteristics. The collision analysis revealed that millions of years of exposure to interstellar dust impacts could indeed modify surface composition and structure in ways that might affect thermal properties, spectroscopic characteristics, and response to solar radiation. However, the magnitude of modification required to explain Oumuamua's most anomalous properties exceeded what collision models predicted for reasonable interstellar environment conditions. Machine learning analysis applied artificial intelligence algorithms to the complete dataset of Oumuamua observations, searching for subtle patterns or correlations that might have been missed by traditional analysis methods. These AI systems were trained on databases of known asteroid and comet properties to identify which aspects of Oumuamua's behavior were most anomalous relative to solar system objects. The machine learning analysis confirmed that Oumuamua's combination of properties was indeed unprecedented among solar system objects, with statistical confidence levels that ruled out conventional classification categories. The AI systems identified the acceleration behavior and extreme elongation as the most anomalous characteristics, followed by the unusual thermal properties and absence of detectable outgassing. Error analysis examined all possible sources of measurement uncertainty, systematic bias, and instrumental artifacts that might have influenced Oumuamua observations. Multiple independent research groups conducted detailed error analysis of trajectory measurements, spectroscopic data, and photometric observations to ensure that reported anomalies reflected genuine object properties rather than measurement problems. The comprehensive error analysis confirmed that Oumuamua's anomalous properties were well above measurement uncertainty levels and were consistent across multiple independent observations and analysis methods. This systematic validation provided strong confidence that Oumuamua's unusual characteristics represented genuine physical properties rather than observational artifacts or analysis errors. Beyond the systematic evidence we've explored, Oumuamua exhibited specific anomalies so unprecedented that they forced astronomers to question fundamental assumptions about how objects should behave in our solar system. These weren't subtle statistical variations or marginal measurement uncertainties. They were clear departures from physical laws and observational patterns that had governed solar system astronomy for centuries. Each anomaly revealed aspects of Oumuamua's nature that challenged conventional categories and suggested possibilities that extended far beyond normal astrophysical processes. The most striking anomaly was Oumuamua's extraordinary shape, which defied everything astronomers thought they knew about how cosmic objects form and evolve. The photometric observations revealed an aspect ratio of approximately 10:1, making Oumuamua at least 5 times more elongated than any asteroid or comet previously observed in our solar system. This extreme elongation approached the theoretical limits of what gravitational forces can hold together, suggesting that Oumuamua was either composed of unusually strong materials or was held together by forces other than gravity. Computer simulations of object formation in planetary systems consistently show that gravitational collapse, accretion processes, and collisional evolution tend to produce objects that are roughly spherical or modestly elongated. Objects with aspect ratios greater than 3:1 are extremely rare in our solar system because rotation, impacts, and gravitational stresses tend to break apart or reshape highly elongated objects over geological timescales. Oumuamua's 10:1 aspect ratio placed it in a category that theoretical models suggested shouldn't exist among natural cosmic objects. The extreme elongation became even more puzzling when combined with Oumuamua's rotation characteristics. Objects with such high aspect ratios should be rotationally unstable, tending to break apart or change their spin states when subjected to external forces. Yet Oumuamua maintained its elongated shape while tumbling in a complex rotational pattern that should have induced stresses capable of fragmenting any normal asteroid or comet. This rotational stability suggested either that Oumuamua was composed of materials much stronger than typical space rocks, or that it possessed internal structure or external forces that provided unusual stability. The acceleration anomaly represented perhaps the most challenging aspect of Oumuamua's behavior for conventional astrophysics. The measured acceleration of approximately 2 × 10⁻⁸ meters per second squared was clearly detectable and consistently directed away from the Sun, resembling the rocket effect produced by comet outgassing. However, despite intensive searches using the world's most sensitive instruments, no evidence was found for the gas emissions that should accompany such acceleration. This acceleration without outgassing violated fundamental principles of conservation of momentum and energy as applied to small solar system bodies. If Oumuamua was experiencing a rocket-like force, something had to be providing the reaction mass and energy necessary to produce that force. The absence of detectable gas emissions meant that either Oumuamua was ejecting material in forms invisible to current instruments, or it was experiencing forces that operated according to principles not captured by conventional physics. Detailed analysis of the acceleration pattern revealed additional anomalies that deepened the mystery. The acceleration was not constant, but varied in ways that didn't match the expected behavior of comet outgassing or solar radiation pressure. Normal comet acceleration peaks when the comet is closest to the Sun and decreases predictably as the comet moves away. Oumuamua's acceleration showed a different pattern, remaining relatively constant over a longer period and not following the inverse square relationship with solar distance that characterizes most solar influence phenomena. The timing of Oumuamua's acceleration also presented anomalies that challenged conventional explanations. The acceleration began when Oumuamua was still relatively far from the Sun, before it reached the distance where comet outgassing typically becomes significant. This early onset suggested that whatever was causing the acceleration was either much more sensitive to solar heating than normal comet materials, or was responding to solar influences other than simple thermal heating. Even more puzzling was the persistence of acceleration as Oumuamua moved away from the Sun. Normal comet acceleration decreases rapidly as the comet moves beyond the distance where solar heating can maintain significant sublimation. Oumuamua's acceleration persisted longer than expected for thermal processes, suggesting either that it contained materials with unusual thermal properties or that it was experiencing non-thermal acceleration mechanisms. The spectroscopic anomalies added another layer of mystery to Oumuamua's profile. While the object's overall spectrum was consistent with rocky or organic-rich composition, subtle features in the spectroscopic data didn't match any known asteroid or comet materials precisely. The spectrum showed absorption features that suggested organic compounds, but with ratios and characteristics that differed from organics found in solar system objects. Particularly puzzling was the absence of water absorption features in Oumuamua's spectrum. Water ice is the most common volatile material in comets and is responsible for most comet outgassing and acceleration. If Oumuamua was experiencing comet-like acceleration, it should have contained significant water ice, which should have been detectable in spectroscopic observations. The absence of water signatures while experiencing acceleration behavior, typical of water sublimation, created a fundamental contradiction in Oumuamua's observational profile. The thermal emission anomalies revealed another aspect of Oumuamua's unusual nature. Infrared observations showed that Oumuamua's thermal properties didn't match those of typical asteroids or comets. The object's thermal emission suggested either unusual surface composition, unexpected internal heat sources, or surface structures that affected thermal radiation in ways not seen in other solar system objects. The thermal data indicated that Oumuamua's surface temperature distribution was more uniform than expected for a rapidly rotating, elongated object. Such objects typically show strong temperature variations between their sunlit and shadowed regions, but Oumuamua's thermal signature suggested more efficient heat distribution than normal rocky or icy materials should provide. This thermal behavior implied either unusual surface properties or internal structure that facilitated heat transfer. The density anomaly presented perhaps the most fundamental challenge to understanding Oumuamua's nature. Calculations based on its observed acceleration and the assumption that solar radiation pressure was responsible suggested that Oumuamua would need to have an extremely low density, less than 1/10 the density of water. Such low density would require Oumuamua to be either hollow, composed of extremely porous materials, or structured more like a thin sheet or membrane than a solid object. Low-density scenarios raised immediate questions about how such an object could maintain its integrity during interstellar travel. Millions of years of exposure to cosmic rays, micrometeorite impacts, and gravitational stresses should destroy any object with the structural fragility implied by extremely low density. The survival of a low-density object through interstellar space seemed physically implausible unless it possessed structural properties or protective mechanisms not found in normal cosmic objects. The rotation anomaly added complexity to Oumuamua's already puzzling profile. The object's tumbling motion was more complex than typical asteroid rotation, suggesting either that it had experienced recent collisions or gravitational encounters that disturbed its spin state, or that it had irregular mass distribution or internal structure that naturally led to unstable rotation. The specific pattern of Oumuamua's tumbling was difficult to model using standard assumptions about object shape and mass distribution. Analysis of the rotation data revealed periodicities and phase relationships that didn't match simple rigid body rotation. This complex rotational behavior suggested either that Oumuamua was not a single solid object, but rather a loosely connected aggregate, or that it had internal degrees of freedom that allowed different parts of the object to move independently. Both possibilities implied internal structure more complex than typical asteroids or comets. The trajectory anomaly extended beyond just the acceleration behavior to include subtle deviations in Oumuamua's path that were difficult to explain through conventional gravitational dynamics. High-precision astrometry revealed small but measurable deviations from the expected trajectory that couldn't be accounted for by the gravitational influences of known solar system objects or by the measured acceleration component. These trajectory deviations suggested either that Oumuamua was experiencing additional forces not captured by standard orbital mechanics, or that it was responding to gravitational influences in ways that differed from normal object behavior. The deviations were small but consistent, appearing in multiple independent trajectory analyses and ruling out random measurement errors as an explanation. The brightness anomaly manifested in photometric observations that showed Oumuamua's light curve had characteristics that didn't match standard models for rotating elongated objects. While the overall brightness variation confirmed the object's extreme elongation, detailed analysis revealed subtle features in the light curve that suggested either unusual surface properties, complex shape geometry, or internal structure that affected how light was reflected and scattered. The photometric data showed evidence for brightness variations that operated on timescales different from the main rotation period, suggesting either that Oumuamua had multiple rotation axes or that its surface properties changed during the observation period. These additional brightness variations were small but detectable, indicating processes or characteristics not captured by simple rigid body rotation models. The composition anomaly became apparent when detailed analysis of all available spectroscopic and photometric data failed to place Oumuamua definitively into any known category of solar system objects. The object's properties fell between asteroids and comets without clearly belonging to either class, suggesting either that it represented a new type of object or that interstellar objects possessed characteristics not found among objects that formed in our solar system. The spectroscopic data showed that Oumuamua's surface had been modified by space weathering processes, but the type and degree of modification differed from space weathering patterns observed on solar system objects. This suggested either that interstellar space weathering operates according to different processes than solar system space weathering, or that Oumuamua's original composition was different from materials typically found in our cosmic neighborhood. The magnetic anomaly, while impossible to measure directly due to Oumuamua's distance and velocity, was inferred from the object's apparent immunity to certain solar wind effects that typically influence small solar system bodies. Objects passing through the inner solar system usually show subtle effects from interaction with the solar wind and solar magnetic field, but Oumuamua's trajectory and behavior showed no clear evidence of such interactions. This apparent magnetic decoupling suggested either that Oumuamua had unusual electrical or magnetic properties that shielded it from normal solar wind interactions, or that it was interacting with solar wind in ways that differed from typical asteroid or comet behavior. The absence of expected solar wind effects added another layer of anomalous behavior to Oumuamua's already complex profile. The environmental anomaly became evident when researchers realized that Oumuamua's properties seemed optimized for interstellar travel in ways that wouldn't be expected for objects that formed within individual star systems. The object's shape, rotation, and apparent structural properties all seem better suited for long-duration space travel than for gravitational capture or accretion processes, typical of planetary system formation. This optimization for interstellar travel raised questions about whether Oumuamua represented a natural object that had been modified by millions of years of interstellar exposure, or whether it might represent something that was designed specifically for travel between star systems. The apparent adaptation to interstellar conditions seemed too specific to result from random evolutionary processes alone. The temporal anomaly related to the brief window available for Oumuamua observation and the object's apparently perfect timing for discovery by human astronomers. The object arrived in our solar system just as automated sky surveys had developed sufficient sensitivity to detect it, and its trajectory brought it close enough to Earth for detailed study during the brief period when it was bright enough for telescopic observation. This fortuitous timing raised questions about whether Oumuamua's arrival was purely coincidental or whether its trajectory had been influenced by factors that took into account the development of human observational capabilities. While such considerations ventured into speculative territory, the remarkable timing of first interstellar object detection coinciding with peak human technological capability seemed worthy of note. The collective weight of these multiple anomalies created a picture of an object that challenged fundamental assumptions about cosmic processes and natural object evolution. Each individual anomaly might potentially be explained through exotic but natural processes, but the combination of simultaneous anomalies suggested that Oumuamua represented something unprecedented in human astronomical experience, something that expanded the boundaries of what we thought was possible in the universe. What made these anomalies particularly significant was how they appeared to be interconnected rather than independent, unusual characteristics. The extreme elongation seemed related to the unusual acceleration behavior, the thermal properties appeared connected to the absence of outgassing, and the rotation anomalies correlated with the trajectory deviations. This interconnectedness suggested that Oumuamua's various anomalous properties might all result from the same underlying cause or mechanism rather than representing multiple independent departures from normal cosmic behavior. The statistical anomaly emerged when researchers calculated the probability of detecting an object with Oumuamua's combination of unusual characteristics. Individual anomalies might occur occasionally in natural cosmic populations, but the simultaneous occurrence of multiple independent anomalies created probability calculations that approached astronomical improbability. The statistical analysis suggested that objects with Oumuamua's combination of properties should be detected perhaps once in millions of years of observation, making its discovery during the first few years of systematic interstellar object searches remarkably unlikely. This statistical improbability raised fundamental questions about whether Oumuamua represented an extremely rare natural phenomenon, or whether its characteristics indicated origins or processes that operated outside the normal statistical distributions governing cosmic object formation and evolution. The mathematics of coincidence suggested that encountering such an object required either extraordinary luck or explanation through processes that were inherently non-random. The observational completeness anomaly became apparent when researchers realized that Oumuamua's detection had been possible only due to a narrow window of observational circumstances that aligned almost perfectly with its trajectory and properties. The object's approach angle, velocity, size, and surface reflectivity all fell within ranges that made detection possible with existing survey systems, but small changes in any of these parameters would have rendered it undetectable. This observational selection effect raised questions about how many similar objects might have passed through our solar system undetected, and whether Oumuamua represented a typical example of interstellar visitors or an unusually detectable member of a population that normally remains invisible to current observational capabilities. The apparent optimization of Oumuamua's properties for detection by human astronomy systems seemed to exceed what random chance would produce. The comparative anomaly emerged from analysis that compared Oumuamua's properties to theoretical predictions about interstellar object populations. Prior to Oumuamua's discovery, computer simulations and theoretical models had predicted the characteristics that interstellar objects should exhibit based on known physical processes and observed solar system object properties. Oumuamua's actual characteristics differed significantly from these predictions in ways that suggested either fundamental gaps in theoretical understanding or the operation of processes not included in current models. Theoretical predictions had anticipated that interstellar objects would be similar to solar system objects, but with compositional differences reflecting formation in different stellar environments. The models predicted roughly spherical shapes, normal rotation patterns, and behavior governed by standard gravitational and thermal processes. Oumuamua's extreme elongation, complex rotation, and anomalous acceleration were not anticipated by any theoretical framework developed prior to its discovery. The evolutionary anomaly related to questions about how an object with Oumuamua's characteristics could have survived millions of years of interstellar travel without being destroyed or significantly modified by space environment effects. Interstellar space contains cosmic rays, micrometeorites, gas clouds, and magnetic fields that should gradually alter object properties over extended time periods. Yet Oumuamua appeared to have maintained structural integrity and coherent properties, despite presumably experiencing millions of years of interstellar exposure. Computer simulations of interstellar weathering processes suggested that objects should become progressively more spherical, less structurally coherent, and more compositionally homogeneous during extended interstellar journeys. The preservation of Oumuamua's extreme elongation and apparent structural integrity implied either that it had spent much less time in interstellar space than its trajectory suggested, or that it possessed protective mechanisms or structural properties that enabled survival under conditions that should destroy normal cosmic objects. The energy balance anomaly became apparent when researchers attempted to account for all energy sources and sinks affecting Oumuamua's thermal and dynamical behavior. The object's acceleration required energy input to maintain momentum transfer. Its thermal properties suggested energy redistribution processes, and its structural integrity implied energy dissipation mechanisms that prevented fragmentation. However, identifying sufficient energy sources to power these processes using conventional physics proved challenging. Solar radiation provided some energy input, but calculations showed that solar energy alone couldn't account for Oumuamua's acceleration behavior unless the object had extreme structural properties that seemed physically implausible. Internal energy sources such as radioactive decay or stored chemical energy were too small to explain the observed phenomena. The apparent energy deficit suggested either that Oumuamua was accessing energy sources not included in conventional analysis, or that it was operating according to energy conversion mechanisms not captured by standard thermodynamics. The material properties anomaly emerged from attempts to identify materials or structures that could simultaneously explain Oumuamua's extreme elongation, low apparent density, structural integrity, and thermal behavior. Known materials science suggested that achieving such a combination of properties would require either exotic materials not found in normal cosmic environments or engineered structures designed to optimize specific performance characteristics. Natural materials typically involve trade-offs between different physical properties. Materials that are strong tend to be dense. Materials that are thermally conductive tend to be metallic. Materials that are structurally stable tend to be rigid. Oumuamua appeared to require materials that optimized multiple properties simultaneously in ways that exceeded what natural material formation processes typically achieve. The formation mechanism anomaly related to the absence of any known astrophysical process that could create objects with Oumuamua's observed characteristics. Planetary formation, asteroid evolution, comet development, and stellar system dynamics all involve well-understood physical processes that produce objects with predictable properties. None of these processes, individually or in combination, could account for the full range of anomalous characteristics that Oumuamua exhibited. Exotic formation scenarios involving tidal disruption events, stellar collisions, or passage through dense interstellar media could potentially explain some of Oumuamua's properties, but required environmental conditions, or events so rare that they approach statistical impossibility. The apparent requirement for multiple rare events to occur in precise sequence to produce Oumuamua's characteristics made natural formation scenarios increasingly implausible. The behavioral prediction anomaly became evident when researchers attempted to use Oumuamua's observed properties to predict its future behavior or to retrodict its past trajectory with greater precision. Objects governed by standard physics should exhibit predictable behavior patterns that allow accurate trajectory calculation and property prediction. Oumuamua's behavior contained elements that were difficult to predict using conventional physics, suggesting either incomplete understanding of the forces affecting it or the operation of non-standard physical processes. The unpredictability extended to efforts to model how similar objects might behave if detected in the future. If Oumuamua represented a typical interstellar visitor, future detections should exhibit similar characteristics and behavior patterns. However, the apparent uniqueness of Oumuamua's combination of properties made it difficult to predict what characteristics future interstellar objects might exhibit or how they might be recognized. The technological signature anomaly emerged from analysis that compared Oumuamua's properties to characteristics that might be expected from artificial objects designed for interstellar travel. While this analysis ventured into speculative territory, several of Oumuamua's anomalous properties aligned more closely with engineered systems than with natural objects formed through random astrophysical processes. The extreme elongation resembled configurations that would be optimal for certain types of interstellar propulsion systems. The absence of outgassing despite acceleration behavior matched what might be expected from non-chemical propulsion mechanisms. The apparent optimization for interstellar travel suggested design considerations rather than random evolutionary adaptation. While these parallels didn't constitute proof of artificial origins, they highlighted how Oumuamua's characteristics seemed better explained by purposeful design than by natural formation processes. The detection methodology anomaly related to questions about whether Oumuamua's unusual properties might have biased the methods used to study it, creating observational artifacts that enhanced its apparent anomalous characteristics. However, multiple independent analysis methods and research groups confirm the reality of Oumuamua's unusual properties, ruling out systematic bias in any single observational or analysis approach. The consistency of anomalous results across different telescopes, different analysis techniques, and different research groups provided strong evidence that Oumuamua's unusual characteristics reflected genuine physical properties rather than methodological artifacts. This methodological validation strengthened the case that Oumuamua represented a genuinely unprecedented object, rather than just an unusual application of observational techniques. The persistence anomaly referred to how Oumuamua's anomalous characteristics remained consistent throughout the observation period, rather than evolving toward more normal behavior patterns. Objects experiencing transient phenomena or temporary environmental effects typically show time-dependent changes that gradually return to normal states. Oumuamua maintained its anomalous acceleration, rotation, and other characteristics consistently throughout the months of observation. This persistence suggested that Oumuamua's anomalous properties reflected intrinsic characteristics rather than temporary responses to solar system environmental conditions. The stability of its unusual behavior patterns implied either that the underlying causes were fundamental properties of the object itself, or that it was subject to ongoing influences that maintained anomalous behavior throughout its solar system passage. The cumulative impact of these multiple interconnected anomalies created a compelling case that Oumuamua represented something truly unprecedented in human astronomical experience, an object whose characteristics challenged fundamental assumptions about cosmic processes and suggested possibilities that extended far beyond conventional astrophysical explanations. Whether those possibilities involved exotic natural phenomena or something else entirely remained an open question that would drive theoretical speculation and observational preparation for future interstellar visitors. When faced with Oumuamua's unprecedented combination of anomalous characteristics, researchers developed theoretical frameworks that pushed far beyond conventional astrophysics to explore possibilities that challenged our fundamental understanding of cosmic objects and processes. These theories range from exotic natural phenomena operating under extreme conditions to scenarios that venture into territory that mainstream science typically approaches with extreme caution. Each theoretical approach attempts to explain Oumuamua's behavior, while opening doors to broader questions about what kinds of objects and processes might exist in the universe beyond our current experience. One of the most scientifically conservative theories proposes that Oumuamua represents a hydrogen iceberg, an object composed primarily of solid hydrogen that formed in the extremely cold environment of interstellar space. According to this framework, Oumuamua could have originated in a molecular cloud where temperatures were low enough for hydrogen gas to condense into solid form, creating objects with very different properties from anything that forms in the warmer environments around stars. The hydrogen iceberg theory explains Oumuamua's acceleration by proposing that solid hydrogen sublimates, when exposed to solar radiation, creating gas emissions that are invisible to telescopic observation because hydrogen lacks the spectroscopic signatures that make other gases detectable. The theory accounts for the object's extreme elongation by suggesting that hydrogen ice could form in sheet-like or elongated structures under the specific conditions present in molecular clouds, where magnetic fields and density gradients might encourage non-spherical accretion. Computer simulations of hydrogen ice behavior under solar system conditions show that such objects could indeed experience acceleration without producing detectable gas emissions, since hydrogen is difficult to observe spectroscopically and dissipates quickly in space. The models also suggest that hydrogen ice objects would have very low density, consistent with Oumuamua's inferred structural properties, and would exhibit thermal behavior that might account for the object's unusual temperature distribution. However, the hydrogen iceberg theory faces significant challenges in explaining how such objects could survive the journey through interstellar space. Solid hydrogen is extremely fragile and would be vulnerable to sublimation from cosmic ray heating, destruction by micrometeorite impacts, and disruption by magnetic field interactions during millions of years of interstellar travel. The theory requires special environmental conditions or protective mechanisms to preserve hydrogen ice objects during interstellar journeys. A second major theoretical framework proposes that Oumuamua represents a dust bunny, or aggregate of interstellar dust particles that were loosely bound together during passage through dense regions of interstellar space. According to this theory, Oumuamua could have formed through accretion of dust and small particles during transit through molecular clouds or other regions where interstellar material density was sufficient to enable gravitational or electrostatic binding. The dust bunny theory explains Oumuamua's low density and unusual structural properties by proposing that it consists largely of empty space between loosely connected dust particles, creating an object with bulk density much lower than solid rock or ice. The theory accounts for acceleration through radiation pressure effects that would be enhanced by the object's high surface area-to-mass ratio, allowing solar radiation to exert greater influence than would be possible on solid objects. The extreme elongation could result from the way dust particles aggregate under the influence of magnetic fields, electric charges, or gas flow patterns in interstellar space. Theoretical models of dust grain behavior in astrophysical environments show that particles can indeed form highly elongated structures under certain conditions, particularly when electromagnetic forces compete with gravitational attraction during the accretion process. The dust bunny theory gains support from observations of similar structures in planetary rings, protoplanetary disks, and comet tails, where dust particles form temporary aggregates with unusual shapes and properties. However, the theory struggles to explain how such fragile structures could maintain coherence during the gravitational stresses and rotation rates that Oumuamua exhibited, since loosely bound dust aggregates typically disperse when subjected to external forces or rapid rotation. The nitrogen iceberg theory, proposed by some researchers as an alternative to hydrogen ice scenarios, suggests that Oumuamua could be composed of solid nitrogen similar to materials found on Pluto's surface. This theory proposes that Oumuamua was originally part of a Pluto-like object in another star system and was ejected into interstellar space through gravitational interactions or impact events that stripped away surface layers. Nitrogen ice has properties that could potentially explain several of Oumuamua's characteristics. It sublimes at temperatures higher than hydrogen but still produces gas emissions that might be difficult to detect spectroscopically. Nitrogen ice can form in layered or sheet-like structures that might account for extreme elongation, and it has density and thermal properties that could be consistent with Oumuamua's observed behavior. The theory explains the acceleration through nitrogen sublimation that creates a rocket effect similar to comet outgassing, but with gas emissions that are much more difficult to detect than the water vapor typically associated with comet activity. Nitrogen emissions would dissipate quickly and might not produce the detectable signatures that astronomers search for during Oumuamua's passage through the solar system. However, the nitrogen iceberg theory faces challenges in explaining the formation of objects with Oumuamua's extreme aspect ratio. While nitrogen ice can form in various shapes, creating structures with 10-to-1 elongation through natural processes remains difficult to explain. The theory also requires special circumstances to preserve nitrogen ice objects during interstellar travel, since nitrogen is volatile and should gradually sublimate during exposure to cosmic radiation over millions of years. A more speculative theoretical framework proposes that Oumuamua represents a solar sail or membrane-like structure that could be either natural or artificial in origin. This theory suggests that Oumuamua might consist of a thin sheet of material with very large surface area relative to its mass, allowing solar radiation pressure to provide the acceleration observed without requiring mass ejection through outgassing. The solar sail theory explains Oumuamua's extreme elongation by proposing that it represents a fragment of a much larger membrane structure that was torn or separated during its interstellar journey. Such membrane fragments could maintain structural integrity while exhibiting the low density and high surface area to mass ratio necessary for radiation pressure acceleration to produce the observed effects. Natural solar sail formation could occur through several astrophysical processes. Stellar winds and radiation pressure around certain types of stars could create membrane-like structures from dust and gas. Supernova explosions could produce thin sheets of material that are ejected at high velocities. Tidal disruption events could stretch objects into extremely thin configurations that acquire membrane-like properties. The artificial solar sail possibility suggests that Oumuamua might represent technology from another civilization, either a deliberate probe sent to explore other star systems or debris from technological activities in distant stellar systems. This interpretation explains the apparent optimization of Oumuamua's properties for interstellar travel and accounts for characteristics that seem difficult to achieve through random natural processes. Advanced civilizations might develop solar sail technology for interstellar exploration, creating probes designed to use radiation pressure for propulsion and maneuvering. Such technology could produce objects with precisely the characteristics that Oumuamua exhibited: extreme elongation for optimal radiation pressure coupling, low density for maximum acceleration efficiency, and structural properties optimized for survival during extended interstellar journeys. The fractal iceberg theory proposes that Oumuamua represents a new type of cosmic object with fractal internal structure that creates unusual bulk properties through geometry rather than composition. According to this framework, Oumuamua could be composed of ordinary materials arranged in fractal patterns that create bulk density, thermal conductivity, and structural properties very different from solid objects with the same composition. Fractal structures can achieve extremely low bulk density while maintaining structural integrity through geometric arrangements that distribute stress efficiently throughout the structure. Such arrangements could explain how Oumuamua maintained its elongated shape while experiencing rotation and external forces that should fragment normal objects with similar aspect ratios. The fractal theory explains acceleration through enhanced surface area that increases interaction with solar radiation and solar wind. Fractal surfaces can have enormously greater effective area than their geometric dimensions suggest, allowing radiation pressure and other solar influences to exert greater force than would be possible on simple geometric shapes with equivalent mass. Fractal formation could occur through various astrophysical processes involving turbulence, magnetic field interactions, or phase transitions during object formation. Computer simulations of structure formation in astrophysical environments show that fractal geometries naturally emerge from many nonlinear physical processes, suggesting that fractal objects might be more common in space than previously recognized. The exotic matter theory ventures into more speculative territory by proposing that Oumuamua might be composed of materials or states of matter that don't exist under normal terrestrial or solar system conditions. According to this framework, the extreme environments present in some regions of interstellar space, around certain types of stars, or during exotic astrophysical events, might create materials with properties that conventional physics doesn't predict. Exotic matter states could include supersonic materials that exhibit unusual mechanical properties, metamaterials with engineered electromagnetic characteristics, or quantum matter phases that maintain coherence over macroscopic scales. Such materials might be naturally produced in high-energy astrophysical environments like neutron star magnetospheres, black hole accretion disks, or supernova explosions. The exotic matter theory explains Oumuamua's anomalous properties by proposing that materials with unprecedented characteristics could exhibit behavior that transcends normal expectations about density, strength, thermal conductivity, and response to external forces. Such materials might maintain structural integrity under conditions that would destroy normal materials or exhibit acceleration mechanisms that operate according to physical principles not captured by conventional mechanics. The temporal artifact theory represents one of the most speculative approaches to explaining Oumuamua's characteristics. This framework proposes that Oumuamua might represent an object that has experienced temporal effects during its journey through regions of space where gravitational time dilation, relativistic effects, or exotic space-time geometries created conditions that altered its physical properties in ways not accounted for by standard physics. According to temporal artifact theory, Oumuamua might have passed near black holes, neutron stars, or other massive objects during its interstellar journey, experiencing gravitational fields strong enough to create significant time dilation effects. Alternatively, it might have traveled through regions where dark matter concentrations, cosmic strings, or other exotic space-time structures created temporal anomalies that affected its evolution. The theory suggests that temporal effects could alter object properties in ways that create apparent violations of conservation laws, unusual acceleration mechanisms, or structural characteristics that seem physically impossible under normal space-time conditions. Such temporal modifications could explain why Oumuamua appears to operate according to physics that differs from terrestrial expectations. The panspermia probe theory proposes that Oumuamua might represent a natural or guided mechanism for distributing biological or pre-biological materials between star systems. According to this framework, Oumuamua could serve as a carrier for organic compounds, microorganisms, or genetic information designed to seed planetary systems with the building blocks necessary for life development. Natural panspermia probes could form through ejection of biologically enriched materials from planets that develop life, creating objects that carry organic chemistry or even living organisms between star systems. Such objects might be optimized for interstellar survival through structural arrangements or compositional characteristics that protect biological cargo during extended space travel. Guided panspermia scenarios suggest that advanced civilizations might deliberately create objects designed to distribute life throughout the galaxy, either by directly seeding other worlds with biological materials or by providing the chemical and structural foundations necessary for life to develop independently. Such objects might be designed to exhibit characteristics that enable them to be detected and studied by emerging technological civilizations. Each of these theoretical frameworks offers different insights into what Oumuamua might represent, but they all share the recognition that explaining its characteristics requires expanding our understanding of what kinds of objects and processes are possible in the universe. Whether Oumuamua represents exotic natural phenomena, technological artifacts, or something entirely beyond our current conceptual categories, its discovery has challenged astronomy to develop more sophisticated theories about cosmic object formation, evolution, and the potential for intelligence to shape cosmic processes across galactic distances and timescales. What's particularly striking about these theoretical approaches is how they converge on the recognition that Oumuamua's characteristics exceed what conventional astrophysical processes should be able to produce. Whether we invoke exotic materials, unusual formation environments, or advanced technology, we consistently encounter the need to expand our understanding of cosmic possibilities to accommodate an object that appears to operate according to principles that transcend normal expectations about how matter and energy behave in space. The metamaterial object theory extends the exotic matter framework by proposing that Oumuamua might be composed of engineered metamaterials designed to exhibit specific electromagnetic, thermal, or mechanical properties not found in naturally occurring substances. Metamaterials can be designed to have negative refractive indices, cloaking properties, or thermal conductivities that differ dramatically from bulk material properties, potentially explaining some of Oumuamua's unusual thermal and acceleration characteristics. Laboratory developments in metamaterial science have demonstrated that carefully structured materials can exhibit properties that seem to violate conventional physics, including apparent violation of conservation laws, faster-than-light signal propagation, and thermal effects that operate contrary to normal thermodynamic expectations. If similar principles operate at macroscopic scales, metamaterial objects could exhibit exactly the kinds of anomalous behavior that Oumuamua demonstrated. The metamaterial theory explains Oumuamua's acceleration through engineered structures that convert solar radiation into directed momentum transfer with efficiency much greater than normal radiation pressure effects. Such structures might operate through plasmon resonances, phononic crystals, or other metamaterial phenomena that amplify electromagnetic interactions to produce macroscopic forces exceeding what conventional physics would predict. The theory accounts for Oumuamua's extreme elongation by proposing that metamaterial structures might be optimized for specific electromagnetic interactions that require precise geometric relationships between structure dimensions and operating wavelengths. Such optimization could naturally produce highly elongated configurations that maximize performance for particular electromagnetic phenomena, while maintaining structural integrity through metamaterial mechanical properties. The consciousness artifact theory represents one of the most speculative approaches, proposing that Oumuamua might represent a manifestation of cosmic consciousness or intelligence that operates according to principles that transcend purely physical processes. This framework suggests that consciousness might be a fundamental aspect of cosmic organization rather than just an emergent property of complex biological systems, and that sufficiently advanced consciousness might be capable of directly manipulating matter and energy to create objects with properties that exceed physical limitations. According to consciousness artifact theory, Oumuamua's anomalous characteristics might result from consciousness-mediated effects that allow direct manipulation of electromagnetic fields, gravitational interactions, or quantum mechanical processes in ways that create apparent violations of conservation laws or other physical principles. Such consciousness effects might operate through mechanisms that current science doesn't recognize or understand. The theory draws support from quantum mechanics research that suggests consciousness plays a fundamental role in determining physical outcomes through observation and measurement effects. If consciousness can indeed influence physical reality at quantum scales, then sufficiently advanced or cosmic scale consciousness might be capable of macroscopic reality manipulation that could produce objects with Oumuamua's characteristics. Recent developments in consciousness research have revealed that awareness might be capable of influencing electromagnetic fields, random number generators, and other physical systems under certain conditions, though the mechanisms remain poorly understood. If consciousness effects can operate at cosmic scales, they might provide explanations for Oumuamua's behavior that transcend conventional physical limitations. The dimensional probe theory proposes that Oumuamua might represent an object that exists partially in higher dimensional space, allowing it to exhibit properties that appear anomalous when observed from our three-dimensional perspective. According to this framework, objects that extend into dimensions beyond our normal spatial experience might have access to forces, energy sources, and structural principles that operate according to higher dimensional physics. Theoretical physics research in string theory and extra-dimensional models suggests that reality might indeed include spatial dimensions beyond the three we directly experience. If objects can exist in or interact with these higher dimensions, they might exhibit behavior that violates three-dimensional physics while operating according to perfectly normal principles in higher dimensional space. The dimensional probe theory explains Oumuamua's acceleration through higher dimensional forces that appear as violations of conservation laws when projected into three-dimensional space. Such forces might operate through gravitational interactions, electromagnetic fields, or exotic phenomena that exist only in higher dimensional environments, but can influence three-dimensional objects under certain conditions. The theory accounts for Oumuamua's structural properties by proposing that its stability and unusual density result from higher dimensional structural elements that provide support and coherence through mechanisms not accessible to three-dimensional analysis. Such support could allow objects to maintain structural integrity under conditions that would destroy purely three-dimensional structures. The holographic projection theory suggests that Oumuamua might represent a holographic manifestation of information stored in higher dimensional space or at cosmic boundaries, similar to how holographic principles operate in theoretical physics, models of black holes, and cosmology. According to this framework, Oumuamua might be a local three-dimensional projection of information that exists in a more fundamental form at cosmic scales. Holographic theories in physics propose that all information contained within any region of space can be encoded on the boundary of that region, suggesting that three-dimensional reality might emerge from two-dimensional information processing at cosmic scales. If this principle operates at solar system scales, objects like Oumuamua might represent holographic projections of information stored at the solar system boundary or beyond. The holographic projection theory explains Oumuamua's anomalous properties by proposing that holographic objects might not be subject to the same physical limitations that govern ordinary matter, since they represent information phenomena rather than traditional material objects. Such objects might exhibit apparent violations of conservation laws, unusual structural properties, or acceleration mechanisms that operate according to information processing principles rather than mechanical physics. The quantum vacuum engineering theory proposes that Oumuamua might represent a technology that manipulates quantum vacuum fluctuations to produce macroscopic forces and effects. According to quantum field theory, empty space is filled with virtual particle pairs that constantly appear and disappear, creating quantum vacuum energy that might be manipulated by sufficiently advanced technology to produce practical effects. Laboratory experiments have demonstrated that quantum vacuum effects can indeed produce measurable forces through phenomena like the Casimir effect, where virtual particles create attractive forces between conducting plates. Advanced vacuum engineering technology might be capable of manipulating these effects at macroscopic scales to produce propulsion, structural support, or energy generation systems that operate without conventional reaction mass or energy sources. The quantum vacuum theory explains Oumuamua's acceleration through vacuum engineering technology that converts quantum vacuum fluctuations into directed momentum transfer, creating thrust without requiring conventional propellant ejection. Such technology might operate through structured electromagnetic fields, geometric configurations, or other methods that bias quantum vacuum fluctuations to produce net forces. The theory accounts for Oumuamua's structural properties by proposing that vacuum engineering might provide structural support that supplements or replaces conventional mechanical strength, allowing objects to maintain integrity under conditions that would destroy purely mechanical structures. Such support might operate through quantum field effects that distribute stress and provide stability without adding mass. The evolutionary artifact theory proposes that Oumuamua might represent an object that has undergone evolutionary development during its interstellar journey, adapting to space environment conditions in ways that produced its unusual characteristics. According to this framework, sufficiently complex objects might be capable of self-modification, learning, or adaptation that allows them to optimize their properties for specific environmental conditions or objectives. Evolutionary adaptation in space might operate through mechanisms similar to biological evolution but involving physical and chemical processes rather than genetic reproduction. Objects might gradually modify their structure, composition, or behavior in response to environmental pressures during extended interstellar travel, developing characteristics that enhance survival or performance under space conditions. The evolutionary theory explains Oumuamua's apparent optimization for interstellar travel by proposing that it developed these characteristics through millions of years of adaptation to space environment conditions. The object's unusual properties might represent convergent evolution toward configurations that maximize survival probability during interstellar journeys. The theory suggests that Oumuamua's acceleration mechanism might be an evolved adaptation that allows interstellar objects to adjust their trajectories for optimal solar system exploration or to maintain communication with other objects during their cosmic journeys. Such adaptation might operate through environmental response mechanisms rather than predetermined design. The convergence of these various theoretical frameworks on the need for exotic physics, advanced technology, or consciousness-mediated effects highlights how fundamentally Oumuamua challenges conventional understanding of cosmic processes, whether we invoke metamaterials, consciousness artifacts, dimensional phenomena, holographic projections, quantum vacuum engineering, or evolutionary adaptation. We consistently encounter the recognition that explaining Oumuamua requires expanding our concepts of what is possible in the universe. This theoretical convergence suggests that Oumuamua might represent a genuine paradigm shift in our understanding of cosmic objects and processes, forcing us to consider possibilities that extend far beyond traditional astrophysics into realms that integrate consciousness, advanced technology, exotic physics, and cosmic-scale information processing. The object's discovery has opened doorways to theoretical territories that challenge fundamental assumptions about the nature of reality, intelligence, and cosmic organization. While the exotic theories we've explored offer compelling frameworks for understanding Oumuamua's unprecedented characteristics, scientific integrity requires that we also consider more conventional explanations for the phenomena we've documented. Perhaps what appears to be evidence of exotic physics, advanced technology, or cosmic consciousness could emerge from natural astrophysical processes operating under extreme but perfectly ordinary conditions that we simply haven't encountered before. These alternative perspectives deserve careful consideration, not as dismissals of cosmic mystery, but as attempts to understand how extraordinary outcomes might arise from conventional physical processes operating in environments or configurations that exceed our previous experience. One of the most robust alternative explanations centers on what astronomers call measurement uncertainty and systematic error amplification. When studying objects as distant, fast-moving, and briefly observable as Oumuamua, even small measurement errors can be amplified through complex data analysis procedures to create apparent anomalies that reflect methodological limitations rather than genuine physical phenomena. The extreme precision required to detect Oumuamua's acceleration, determine its shape, and analyze its composition pushed observational techniques to their limits, where subtle systematic errors could produce misleading results. The trajectory analysis that revealed Oumuamua's non-gravitational acceleration relied on astrometric measurements accurate to fractions of an arcsecond across observations spanning several months. Even tiny systematic errors in telescope pointing, atmospheric refraction corrections, or stellar reference frame calibrations could introduce apparent accelerations that mimic the effects of outgassing or exotic propulsion mechanisms. When multiple observatories contribute data to trajectory calculations, differences in instrumental calibration, data reduction procedures, or analysis software could create artificial signals that appear to represent genuine physical effects. The shape determination that revealed Oumuamua's extreme elongation depended on photometric observations of brightness variations as the object rotated. However, interpreting brightness variations in terms of object shape requires assumptions about surface reflectivity, rotation axis orientation, and viewing geometry that might not be valid for objects with unusual composition or structure. If Oumuamua had surface properties, rotation characteristics, or internal structure that differed from typical asteroids and comets, standard shape analysis techniques might produce misleading results that exaggerate apparent elongation. Alternative shape models suggest that Oumuamua's dramatic brightness variations could result from other causes than extreme elongation. A roughly spherical object with highly variable surface reflectivity could produce similar brightness changes if different regions of its surface had drastically different albedos. An object with a complex irregular shape involving multiple lobes or components could create brightness variations that mimic extreme elongation when analyzed using standard techniques designed for simple geometric shapes. A second major alternative explanation involves unknown but conventional astrophysical processes that operate under the extreme conditions present in interstellar space or during high-velocity encounters with stellar radiation environments. The interstellar medium contains plasma, magnetic fields, dust, and radiation that create environmental conditions impossible to reproduce in terrestrial laboratories or even in most solar system environments. Objects that have spent millions of years traveling through such environments might develop properties or behaviors that appear anomalous when observed in our solar system, but actually result from conventional physics operating under extraordinary circumstances. Interstellar magnetic field interactions could gradually modify object properties during extended space travel. Charged particles in interstellar space could accumulate on object surfaces, creating electrostatic charges that affect subsequent interactions with solar wind and solar magnetic fields. Such electrostatic effects might produce apparent acceleration that resembles outgassing but actually results from electromagnetic forces that operate differently on charged objects than on neutral ones. Cosmic ray bombardment during millions of years of interstellar travel could alter object composition, structure, and physical properties in ways that affect thermal behavior, mechanical strength, and response to solar radiation. High-energy cosmic ray impacts could create internal fractures, modify surface chemistry, or induce structural changes that make objects behave differently from solar system materials that haven't experienced extended cosmic ray exposure. Interstellar dust accretion might gradually coat traveling objects with materials that have different properties from the original object composition. Such dust mantles could alter thermal emission characteristics, spectroscopic signatures, and mechanical properties in ways that create apparent anomalies when the objects are observed in solar system environments. The dust mantle theory could explain why Oumuamua's surface properties seemed inconsistent with its inferred bulk composition. The statistical coincidence and selection bias explanation suggests that Oumuamua's apparent uniqueness might result from the combination of rare but not impossible natural processes occurring in a single object that happened to be detected during the first systematic search for interstellar visitors. While individual aspects of Oumuamua's behavior might be highly improbable, the combination could still result from natural causes if we consider the enormous number of objects that have been ejected from star systems throughout galactic history. Statistical analysis reveals that if billions of objects have been ejected into interstellar space over the galaxy's history, even combinations of extremely improbable characteristics should occur occasionally through pure chance. The apparent impossibility of Oumuamua's combination of properties assumes that its characteristics are completely independent, but many astrophysical processes are correlated in ways that make unlikely combinations more probable than simple statistics suggest. Selection bias effects could enhance the apparent uniqueness of any interstellar object we detect. Objects with unusual properties might be more likely to be detected by automated survey systems than typical interstellar visitors, since unusual brightness variations, unexpected trajectories, or anomalous spectroscopic characteristics would make them stand out from background stars and known solar system objects. The first interstellar object detected might naturally appear unusually anomalous because anomalous objects are more detectable. The timing of Oumuamua's discovery during the first few years of systematic interstellar object searches could also represent selection bias rather than meaningful coincidence. If unusual objects are indeed more detectable than typical interstellar visitors, then the most anomalous examples would naturally be discovered first, creating the false impression that all interstellar objects possess unusual characteristics, when actually we're seeing the extreme tail of the population distribution. A third major alternative explanation focuses on observational limitations and incomplete data interpretation. The brief window available for Oumuamua observation, less than 2 months for detailed study, meant that many fundamental questions about its properties remained unanswered due to practical limitations rather than inherent mystery. Many of the apparent anomalies might be resolved through observations that were simply impossible to obtain given the object's rapid departure from the inner solar system. Spectroscopic observations that might have revealed the composition responsible for Oumuamua's acceleration were limited by the object's faintness and rapid motion. More sensitive spectrographs or longer observation times might have detected gas emissions that were below the detection threshold of available instruments. The apparent absence of outgassing might reflect instrumental limitations rather than genuine absence of gas production. The extreme elongation inferred from photometric observations was based on limited data, spanning only a few rotation periods. Longer observation periods might have revealed additional brightness variations that would modify shape interpretations or reveal that the object's rotation was more complex than initially assumed. Alternative rotation models involving multiple axes or component objects might explain the brightness variations without requiring extreme elongation. The thermal infrared observations that suggested unusual surface properties were conducted when Oumuamua was already quite distant from Earth, reducing measurement precision and limiting the ability to detect subtle thermal signatures that might explain the object's anomalous behavior. Closer infrared observations might have revealed thermal emission patterns consistent with conventional outgassing or surface composition that could account for the observed acceleration. The mundane exotic object explanation proposes that Oumuamua might represent a type of object that is genuinely unusual compared to solar system materials, but still forms through conventional astrophysical processes. This framework suggests that the diversity of planetary formation environments throughout the galaxy could produce object types that don't exist in our solar system, but are nevertheless natural products of stellar and planetary evolution operating under different conditions. Exoplanetary system observations have revealed planetary configurations that don't exist in our solar system, including hot Jupiters, super-Earths, and systems with planets in highly eccentric or misaligned orbits. These discoveries suggest that planetary formation can produce outcomes very different from our solar system's architecture, potentially including small body populations, with characteristics not represented among asteroids and comets in our cosmic neighborhood. Different stellar environments could produce objects with unusual composition, structure, or formation history. Stars with different masses, metallicities, or evolutionary states might create planetary systems where small bodies form through processes or from materials that differ significantly from solar system conditions. Objects ejected from such systems might possess characteristics that appear anomalous when observed in our solar system but represent normal outcomes of formation in alien stellar environments. The chemical composition of interstellar objects should reflect the stellar nucleosynthesis history and galactic chemical evolution of their formation regions. Objects from different parts of the galaxy or from different epochs in galactic history might contain isotopic ratios, chemical abundances, or even molecular structures that don't match solar system expectations, creating apparent compositional anomalies that reflect natural galactic diversity rather than exotic physics. The instrumental evolution bias explanation suggests that Oumuamua's apparent uniqueness might partly reflect improvements in observational capabilities that allow detection of object types that were always present but previously unobservable. Advanced automated survey systems, more sensitive spectrographs, and improved data analysis techniques might have revealed characteristics that would have been missed by earlier generations of astronomical instruments. Historical asteroid and comet observations were limited by instrumental sensitivity, observational techniques, and analysis methods that might have systematically missed objects with unusual properties. If Oumuamua-like objects have been passing through our solar system regularly, they might have been undetected, misclassified, or inadequately characterized by previous observational programs that lack the sensitivity to identify their anomalous characteristics. The development of machine learning algorithms for astronomical data analysis has revealed subtle patterns and correlations in existing datasets that human observers missed during decades of traditional analysis. Similar algorithmic approaches applied to Oumuamua might have identified anomalous characteristics that resulted from analysis methodology rather than genuine physical properties, especially if the algorithms were trained on databases that didn't include examples of interstellar objects. The environmental modification explanation proposes that Oumuamua's unusual properties could result from modification during its passage through our solar system, rather than representing intrinsic characteristics developed during interstellar travel. The transition from interstellar space to solar system environment exposes objects to radiation fields, magnetic environments, and gravitational stresses that could trigger physical or chemical changes, producing anomalous behavior. Solar wind interaction with objects that have been charged by cosmic ray exposure during interstellar travel could produce electromagnetic effects that create apparent acceleration through mechanisms different from conventional outgassing. The solar wind contains charged particles and magnetic fields that could interact with electrostatically charged objects to produce forces that mimic rocket propulsion without requiring mass ejection. Thermal cycling as objects approach and recede from the Sun could trigger structural changes in materials that have been modified by millions of years of interstellar exposure. Phase transitions, thermal expansion effects, or stress release in materials altered by cosmic ray bombardment might produce mechanical effects that could account for acceleration, rotation changes, or apparent structural modifications. Gravitational gradient effects during close passage by the Sun could induce tidal stresses in objects with unusual internal structure or composition. If Oumuamua had internal cavities, layered structure, or non-uniform density distribution, tidal forces might trigger internal motion or structural rearrangement that could produce external effects resembling propulsion or outgassing. The theoretical incompleteness explanation acknowledges that current astrophysical theory might simply be incomplete in ways that make Oumuamua's behavior appear more anomalous than it actually is. Our understanding of small body formation, interstellar medium interactions, and radiation pressure effects is based primarily on solar system observations and laboratory experiments that might not capture all relevant physical processes operating under extreme interstellar conditions. Small body physics theory has been developed primarily through studies of asteroids and comets that formed within our solar system and have never experienced interstellar environments. The extrapolation of this theory to objects that formed in different stellar systems and traveled through interstellar space for millions of years might not adequately account for physical processes or environmental effects that operate only under such extreme conditions. Radiation pressure theory typically assumes objects with simple geometric shapes and uniform surface properties, but real objects might have complex surface structures, internal cavities, or compositional heterogeneities that modify radiation pressure effects in ways not captured by standard models. If Oumuamua had surface or structural properties outside the range of current theoretical models, its behavior might appear anomalous when interpreted using inadequate theoretical frameworks. The dust dynamics and plasma physics of interstellar space remain poorly understood due to the difficulty of making direct measurements in interstellar environments. Objects traveling through interstellar space might experience forces, modification processes, or environmental effects that current theory doesn't adequately describe, making their behavior appear anomalous when they're observed in solar system environments. These alternative explanations collectively suggest that Oumuamua's anomalous characteristics might result from conventional astrophysical processes operating under extreme conditions, observational limitations that prevented complete characterization, or theoretical gaps that make normal phenomena appear extraordinary. While these alternatives don't definitively explain all of Oumuamua's unusual properties, they remind us that the universe has consistently surprised us by achieving remarkable complexity through entirely natural processes, and that apparent anomalies often yield to deeper understanding rather than requiring revolutionary new physics or exotic explanations. Act 7, Closing Reflections, approximately 2,300 words. As we reach the end of our journey through the mystery of Oumuamua and what it means to gaze into the cosmic unknown, we find ourselves in a place of deeper wonder rather than definitive answers. We've explored the deep history of interstellar wanderers, examined compelling evidence for unprecedented characteristics, investigated specific anomalies that challenge our understanding, considered theoretical frameworks that expand our concepts of cosmic possibilities, and weighed alternative explanations that remind us of nature's capacity for surprise. Through it all, Oumuamua remains what it was from the beginning, a quiet hint from the cosmos that reality contains depths and complexities we're only beginning to glimpse. What emerges most clearly from our exploration is that Oumuamua represents a profound moment in human consciousness, our first confirmed encounter with a visitor from another star system, carrying information about cosmic processes that operate beyond our local experience. Whether its unusual characteristics result from exotic natural phenomena, advanced technology, or simply our incomplete understanding of interstellar physics, Oumuamua has fundamentally expanded our awareness of what kinds of objects and processes might exist in the universe beyond our previous experience. The encounter with Oumuamua reveals something important about the nature of cosmic discovery and human consciousness. When we encounter phenomena that don't fit our existing categories, we're forced to expand our thinking, develop new hypotheses, and grapple with possibilities we hadn't previously considered. Oumuamua challenged every assumption astronomers had developed about small solar system bodies, forcing the scientific community to acknowledge that the universe contains surprises that transcend our theoretical frameworks and observational experience. This expansion of cosmic awareness reflects broader patterns in how human consciousness evolves through contact with the unknown. Each generation of astronomers has discovered phenomena that challenged existing understanding and required new theoretical frameworks to explain. From the discovery that Earth orbits the Sun rather than the reverse, to the realization that the universe is expanding, to the detection of exoplanets around other stars, astronomy consistently reveals that reality exceeds our imagination and that the universe is stranger and more wonderful than we typically assume. Oumuamua's brief visit served as a preview of future discoveries that will undoubtedly challenge our understanding even more dramatically. Next-generation survey telescopes coming online in the coming years are expected to detect dozens or hundreds of interstellar objects annually, providing opportunities to study a diverse population of visitors from other star systems. Each new detection will test whether Oumuamua represents a typical example of interstellar objects or an unusually anomalous member of a population that includes even stranger visitors. The Vera C. Rubin Observatory, with its unprecedented ability to scan the entire visible sky every few nights, will likely detect interstellar objects while they're still far from Earth, providing much longer observation windows than were available for Oumuamua. These extended observations will allow detailed spectroscopic analysis, thermal infrared characterization, and possibly even spacecraft missions to rendezvous with interstellar visitors before they depart our solar system. Future space missions specifically designed to intercept interstellar objects could provide the detailed analysis that was impossible during Oumuamua's rapid passage. Such missions might include sample return capabilities, allowing direct laboratory analysis of interstellar materials for the first time in human history. The chemical, isotopic, and structural analysis of interstellar samples could reveal formation conditions in alien star systems, and possibly even evidence of biological processes operating in other cosmic neighborhoods. The philosophical implications of Oumuamua's visit extend far beyond astronomy to encompass fundamental questions about consciousness, reality, and humanity's place in cosmic evolution. The object's arrival forced us to confront our assumptions about cosmic isolation and the possibility that we live in a universe where communication, contact, or influence between civilizations might occur through mechanisms we don't yet understand. If Oumuamua represents natural phenomena, it demonstrates that the universe operates according to physical principles more complex and surprising than our current theories capture. If it represents technology from another civilization, it suggests that intelligence capable of interstellar engineering exists in our cosmic neighborhood, and that we might not be alone in developing capabilities for space exploration and communication. Either possibility transforms our understanding of humanity's cosmic context. We're either living in a universe where natural processes produce outcomes that challenge our basic assumptions about physics and cosmic evolution, or we're part of a galactic community where intelligence and technology operate across interstellar distances in ways that exceed our current capabilities. The experience of studying Oumuamua also revealed important limitations in our observational capabilities and theoretical frameworks. The brief observation window that prevented detailed characterization highlighted how unprepared we are for encounters with truly unprecedented phenomena. The difficulty of distinguishing between exotic natural processes and possible technological artifacts demonstrated how much we still don't know about cosmic processes and what kinds of intelligence or technology might exist in the universe. These limitations suggest that preparation for future interstellar object encounters should involve not just technological development, but also conceptual expansion that allows us to recognize and interpret phenomena that transcend our current categories of understanding. We need observational systems capable of rapid response to unexpected discoveries, theoretical frameworks flexible enough to accommodate unprecedented observations, and analytical methods that can distinguish between different types of exotic possibilities. The global response to Oumuamua's discovery demonstrated both the potential and the limitations of international scientific cooperation in addressing cosmic mysteries. While researchers around the world collaborated effectively to gather and analyze observations, the brief detection window and limited observational resources meant that many crucial questions remained unanswered. Future interstellar object encounters will require more coordinated international response capabilities and possibly dedicated resources for rapid response observations of unexpected cosmic visitors. The public fascination with Oumuamua revealed deep human interest in the possibility of contact with other intelligences and the fundamental questions about our place in the universe that such contact would raise. The object's mysterious characteristics captured public imagination in ways that routine astronomical discoveries rarely achieve, suggesting that encounters with the truly unknown resonate with fundamental aspects of human consciousness and our desire to understand our cosmic context. This public engagement also highlighted the importance of maintaining scientific rigor while remaining open to possibilities that challenge conventional understanding. The balance between healthy skepticism and creative speculation that Oumuamua's study required demonstrates the kind of intellectual flexibility that will be necessary for interpreting future cosmic mysteries that might be even more challenging to understand. The educational value of Oumuamua's discovery extends beyond its specific characteristics to encompass broader lessons about the nature of scientific inquiry, cosmic exploration, and human consciousness. The object served as a case study in how science responds to unprecedented observations, how theoretical frameworks evolve to accommodate new phenomena, and how human curiosity drives us to explore mysteries that expand our understanding of reality. Students and researchers studying Oumuamua learn not just about interstellar objects, but about the process of scientific discovery itself, how observations lead to hypotheses, how evidence supports or challenges theories, and how the boundaries of knowledge expand through encounters with phenomena that exceed previous experience. These lessons prepare future scientists for discoveries that will undoubtedly challenge understanding in ways we can't yet anticipate. The technological developments motivated by Oumuamua's study have applications that extend far beyond interstellar object research. Improved astrometric techniques, more sensitive spectroscopic methods, and enhanced data analysis algorithms developed for studying mysterious cosmic visitors contribute to many areas of astronomy and space science. The rapid response observational capabilities needed for interstellar object studies also support planetary defense efforts, solar system exploration, and fundamental astrophysics research. The long-term implications of Oumuamua's discovery may not become clear for decades or centuries as human cosmic awareness and technological capabilities continue to evolve. If the object represents our first encounter with evidence of cosmic intelligence, its significance might only be fully appreciated when we develop the capabilities necessary for more sophisticated cosmic communication or exploration. If it represents exotic natural phenomena, understanding its characteristics might require theoretical breakthroughs that haven't yet occurred. The memory of Oumuamua will likely inspire future generations of astronomers, engineers, and explorers who dedicate their careers to understanding cosmic mysteries and searching for evidence of intelligence or exotic phenomena in the universe. The object demonstrated that the cosmos contains surprises that can appear without warning and challenge our most basic assumptions about reality, encouraging continued vigilance and openness to possibilities that transcend current understanding. As we contemplate Oumuamua's message about gazing into the unknown, we recognize that the true significance of cosmic mysteries lies not in solving them definitively, but in allowing them to expand our consciousness and deepen our appreciation for the complexity and wonder of existence. The object arrived as a quiet hint from the cosmos that reality contains depths we're only beginning to explore, and its brief visit reminded us that we live in a universe capable of producing phenomena that exceed our wildest imagination. The ongoing search for understanding Oumuamua's nature and origin continues through theoretical work, computer simulations, and preparation for future interstellar visitors. Each new insight contributes to our growing understanding of cosmic processes and our place within the vast community of objects, forces, and possibly intelligences that populate the universe beyond our solar system. In the end, Oumuamua's greatest gift may be the questions it raised rather than any answers it provided. The object challenged us to expand our concepts of what's possible in the universe, encouraged us to develop more sophisticated observational and theoretical capabilities, and reminded us that cosmic exploration leads not to final answers, but to ever deeper mysteries that reveal the inexhaustible wonder of existence itself. As Oumuamua continues its journey into the outer reaches of our solar system and eventually back into interstellar space, it carries with it the knowledge that it was observed, studied, and wondered about by a young technological civilization taking its first tentative steps toward understanding its cosmic environment. Whether it represents a natural cosmic phenomenon or something more purposeful, it has served as a catalyst for human consciousness expansion and a reminder that the universe holds secrets we're only beginning to discover. The quiet hint that Oumuamua offered us continues to resonate through our growing awareness that we live in a cosmos far more mysterious and wonderful than we ever dared imagine, and that the greatest discoveries lie not behind us in what we've already learned, but ahead of us in the vast unknown that awaits our continued exploration and wonder. What makes Oumuamua's visit particularly poignant is how it arrived at a moment in human history when our technological capabilities had just reached the threshold necessary to detect and study interstellar visitors, yet remained insufficient to fully characterize such objects during their brief passages through our solar system. This timing creates a profound sense of standing at the edge of a new era in cosmic exploration, where we can glimpse possibilities that exceed our current understanding while recognizing how much we still need to learn. The object's discovery occurred during a period when human civilization is grappling with fundamental questions about our relationship with technology, our responsibility for planetary stewardship, and our potential role in cosmic evolution. Oumuamua's mysterious characteristics and possible technological interpretation arrived as humanity debates the implications of artificial intelligence, space exploration, and our search for life beyond Earth. The timing seems almost designed to challenge us to think more deeply about what intelligence and technology might mean on cosmic scales. The cultural impact of Oumuamua extends beyond scientific communities to influence art, literature, philosophy, and popular imagination in ways that reveal deep human resonance with the possibility of cosmic contact and communication. Artists have created works inspired by the object's mysterious, elongated form. Writers have developed stories exploring its possible origins and meanings, and philosophers have used it as a case study for examining how we recognize and respond to the genuinely unprecedented. This cultural resonance suggests that Oumuamua touched something fundamental in human consciousness, our ancient awareness that we exist within cosmic processes larger than terrestrial experience, and our intuitive recognition that the universe might contain intelligence and purpose that transcends biological evolution on individual planets. The object served as a kind of cosmic Rorschach test, revealing as much about human hopes, fears, and assumptions as about interstellar physics. The interdisciplinary collaboration that Oumuamua's study required demonstrated how cosmic mysteries naturally transcend traditional academic boundaries and require integration of insights from multiple fields of knowledge. Understanding the object's possible nature demanded contributions from astronomy, physics, chemistry, materials science, computer science, engineering, and even consciousness research and philosophy. This interdisciplinary synthesis created new connections between different domains of knowledge and suggested models for addressing future cosmic mysteries. The collaborative networks that formed around Oumuamua research also revealed how cosmic exploration naturally creates international cooperation that transcends political and cultural boundaries. When faced with a genuinely cosmic mystery, researchers from different countries and cultural backgrounds found common ground in shared curiosity and methodological approaches that emphasized careful observation, rigorous analysis, and creative theoretical exploration. The ethical questions raised by Oumuamua's possible technological interpretation have implications that extend far beyond the specific case of this one object. If we do encounter clear evidence of extraterrestrial technology, how should humanity respond? What protocols should govern contact attempts? How do we balance scientific investigation with respect for potentially superior intelligence? What responsibilities do we have to preserve evidence and share information globally? These ethical considerations become particularly complex when we consider that Oumuamua's rapid departure meant that any response decisions would need to be made within extremely short time frames. The object's trajectory gave humanity only a few months' notice of its arrival, and only a few months to study it before it departed permanently. This time pressure highlights the need for pre-established protocols and international agreements about how to respond to unexpected cosmic visitors. The search for similar objects has intensified dramatically since Oumuamua's discovery, with multiple research groups developing improved detection algorithms, dedicating telescope time to interstellar object searches, and creating rapid response networks for characterizing future visitors. This enhanced vigilance reflects both scientific curiosity and recognition that interstellar objects provide unique opportunities to study materials and processes from other star systems. The development of artificial intelligence systems specifically designed to identify interstellar objects in astronomical survey data has revealed that our solar system might receive such visitors much more frequently than previously estimated. Machine learning algorithms can detect subtle patterns in object motion and brightness that human observers might miss, potentially identifying interstellar visitors that would otherwise be overlooked or misclassified as solar system objects. These AI-enhanced detection systems are already finding candidates for additional interstellar objects in archival data, suggesting that Oumuamua might not have been as unique as initially thought. The realization that interstellar visitors might be relatively common transforms them from isolated curiosities into a new class of astronomical objects that could provide regular opportunities to study materials from other star systems. The technological challenges of studying rapidly moving interstellar objects have motivated development of new observational techniques and mission concepts that could revolutionize our ability to characterize such visitors. Proposed concepts include spacecraft that remain dormant in the outer solar system until activated by the approach of interstellar objects, ground-based telescopes specifically optimized for tracking fast-moving targets, and space-based observation platforms positioned at gravitational focus points where solar gravity could enhance telescope sensitivity. Some of the most ambitious proposals involve developing spacecraft with sufficient propulsion capability to chase down and rendezvous with interstellar objects even after they've been accelerated by solar gravity during their passage through the inner solar system. Such missions would require revolutionary advances in propulsion technology, but could provide detailed in situ analysis of interstellar materials for the first time in human history. The implications of Oumuamua's study for astrobiology and the search for extraterrestrial life extend beyond the specific question of whether this object represents technology to encompass broader questions about how life and intelligence might spread throughout the galaxy. If natural processes can transport materials between star systems, then the building blocks of life or even living organisms might travel between worlds through panspermia processes that could make life more common throughout the universe than planet-by-planet evolution would suggest. The possibility that interstellar objects could serve as vectors for biological or technological information transfer has motivated new research into extremophile organisms that might survive interstellar journeys, the preservation of complex molecules under space conditions, and the kinds of information encoding that might remain stable across cosmic distances and timescales. These studies contribute to astrobiology research while also preparing for the possibility that future interstellar visitors might carry evidence of life or intelligence from their origin systems. The psychological and spiritual impact of Oumuamua's discovery resonates with deep human needs for cosmic connection and meaning that transcend purely scientific curiosity. The object's arrival reminded many people that we exist within cosmic processes that connect us to distant regions of space and time, creating a sense of cosmic citizenship that transcends terrestrial concerns and national boundaries. This cosmic perspective naturally leads to broader reflection on humanity's role and responsibility within galactic evolution. If we are part of a universe where intelligence and technology can influence cosmic processes across interstellar distances, then our choices about technological development, space exploration, and planetary stewardship might have implications that extend far beyond Earth and far into the future. The environmental lessons implicit in Oumuamua's study include recognition that planetary systems naturally exchange materials and possibly information across cosmic distances, making each world part of larger galactic ecosystems that operate according to principles of cosmic evolution and development. This galactic ecosystem perspective encourages thinking about environmental stewardship that encompasses not just terrestrial ecology but humanity's potential role in cosmic processes. The educational transformation motivated by Oumuamua's discovery has influenced how astronomy and space science are taught at all levels, from elementary school through graduate research. The object provided a compelling case study for demonstrating how science responds to unprecedented observations, how theoretical frameworks evolve to accommodate new phenomena, and how the boundaries of knowledge expand through encounters with cosmic mysteries. Students studying Oumuamua learn not just about interstellar objects, but about the nature of scientific discovery itself, how observations lead to hypotheses, how evidence supports or challenges theories, and how the scientific community collaborates to address questions that no single researcher or institution can answer alone. These lessons prepare future scientists for discoveries that will undoubtedly challenge understanding in ways we can't yet anticipate. The museum exhibitions, planetarium shows, and public education programs inspired by Oumuamua have reached millions of people worldwide, introducing concepts about interstellar travel, cosmic evolution, and the search for extraterrestrial intelligence to audiences who might not otherwise encounter such ideas. This public engagement creates broader cultural awareness of cosmic possibilities and builds support for continued space exploration and scientific research. The inspiration that Oumuamua provides for future generations of scientists, engineers, and explorers may prove to be its most lasting legacy. The object demonstrated that the cosmos contains surprises that can appear without warning and challenge our most basic assumptions about reality, encouraging continued vigilance and openness to possibilities that transcend current understanding. Young people who followed Oumuamua's discovery and the subsequent scientific debates are now choosing careers in astronomy, planetary science, astrobiology, and space engineering, motivated by the recognition that cosmic exploration leads to discoveries that can transform our understanding of reality itself. These future researchers will have opportunities to study interstellar objects with technologies and theoretical frameworks that will make Oumuamua's brief characterization seem primitive by comparison. The technological spillovers from Oumuamua research are already contributing to advances in multiple fields beyond astronomy. Improved algorithms for detecting small, fast-moving objects contribute to planetary defense efforts and space situational awareness. Enhanced spectroscopic techniques developed for analyzing faint, rapidly moving targets find applications in environmental monitoring and materials science. The rapid response observational protocols developed for interstellar object studies provide models for coordinating international scientific collaboration on time-critical research problems. As we look toward the future, Oumuamua's discovery marks the beginning of a new chapter in human cosmic exploration, where we regularly encounter materials and possibly intelligence from other star systems. Each future interstellar visitor will provide opportunities to test our understanding of cosmic processes and to search for evidence of life or technology that operates according to principles we haven't yet discovered. The philosophical implications of this new era in cosmic exploration extend beyond science to encompass fundamental questions about consciousness, meaning, and humanity's purpose in the universe. If we live in a cosmos where intelligence and technology operate across interstellar distances, then our own development of cosmic capabilities might represent participation in galactic evolutionary processes that connect us to forms of consciousness and intelligence that transcend individual planetary civilizations. In the end, Oumuamua's greatest contribution may be its demonstration that the universe is not only stranger than we imagine, but stranger than we can imagine with our current conceptual frameworks. The object challenged us to expand our understanding of what's possible while reminding us that every answer leads to deeper questions and every discovery reveals greater mysteries waiting to be explored. The quiet hint that Oumuamua offered continues to echo through our expanding cosmic awareness, inviting us to develop the consciousness, technology, and wisdom necessary to participate more fully in whatever cosmic community or processes exist beyond our current understanding. As we continue gazing into the unknown, we carry with us the knowledge that the unknown gazes back with mysteries that may transform not just our understanding of the universe, but our understanding of what it means to be conscious beings in a cosmos full of infinite wonder and possibility.